Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about the module Orbital Angular Momentum and Spherical Harmonics under the paper Quantum Mechanics 1. So students, let us see what we are going to learn in this module. Firstly, we'll start with the discussion of the representations of the orbital angular momentum operators in spherical polar coordinates. Then we'll move on to discussing the eigenfunctions and the eigenvalues of the operators L square and operator Lz. From there, we'll study about the important properties of spherical harmonics. Then the discussion will move on to the physical interpretation of the eigenvalues of the operators L square and Lz. And finally, we'll discuss about the properties of the ladder operator L plus and L minus. So we will begin with the discussion of the results that we had obtained in the preceding modules with respect to the angular momentum operators, and we will see that discussion was basically deduced from the general definition of the angular momentum and the general properties of vectors and operators in Hilbert space. Using those concepts, we are now going to turn our attention to discuss the properties of the orbital angular momentum representation. And we will discuss that as a classical counterpart, it indicates that how the orbital motion of particle arises. So basically what we are going to do is we're going to start with the formalism similar to what we developed for the angular momentum operator J, and then we'll try and implement that formalism onto the orbital angular momentum operators L and its different components, that is the xyz components, operator Lx, Ly and Lz, then the L square component, and also finally the ladder components, that is the L plus operator and the L minus operator. We will also see that while developing these formalisms, the orbital angular momentum operator can be represented in the form of spherical harmonics, and that is going to be interesting because when we will represent it as spherical harmonics, we will also see that a periodicity gets built into the formalism. Angular momentum operators. Now let us discuss the different components of the orbital angular momentum operators, both in the Cartesian coordinate system as well as in the spherical polar coordinate systems. So we will begin our discussion with first considering the components of the orbital angular momentum operators in the Cartesian coordinate system. In this system, the components of the orbital angular momentum operators are Lx, operator Lx, which is the x component, operator Ly, which is the y component, and operator Lz, which is the z component. So in Cartesian coordinate system, operator Lx is represented as minus iota times h cross within brackets y times del by del z, or differentiation with respect to z, minus z times partial differentiation with respect to y. And the x component of the orbital angular momentum operator in the spherical polar coordinates is represented as operator Lx is equal to iota times h cross times within bracket sine phi partial differentiation with respect to theta plus cot theta cos phi times partial differentiation with respect to phi. Here theta and phi denote the angles of the orbital or of the spherical polar coordinate systems. That is, that while phi denotes the angle that the orbital angular momentum vector makes with the z-axis, theta gives the angle of the projection of the orbital angular momentum vector on the xy plane with the x-axis. Now, similarly, we can define the y component of the orbital angular momentum operator Ly is equal to minus iota times h cross times within bracket z times partial differentiation with respect to x minus x times partial differentiation with respect to z. This is the representation in the Cartesian coordinate system, and the representation in the spherical polar coordinate system is given as operator Ly is equal to iota times h cross times within brackets minus cos phi times partial differentiation with respect to theta plus cot theta sin phi times partial differentiation with respect to phi, where, as defined earlier, angles theta and phi are the angles of the spherical polar coordinate system, and the z component of the orbital angular momentum operator Lz is equal to minus h cross times x times partial differentiation with respect to y minus y times partial differentiation with respect to x. This is the representation in Cartesian coordinate system, and operator Lz is equal to minus iota times h cross times partial differentiation with respect to phi. This is the representation in the spherical polar coordinate system. And finally, we get the result that the orbital angular momentum operator L square is equal to Lx square, operator Lx square plus operator Ly square plus operator Lz square, where operator Lx is the x component of the orbital angular momentum operator, Ly the y component, and Lz the z component. Now we can express the operator L square and the operators Lx square, Ly square, and the Lz square in terms of the operators R and operator P, where R is the radial operator or the radial vector, and operator P is the momentum operator or the momentum vector. So we know that operator L square is equal to vector R square times vector P square minus vector R dot vector P whole square, where R dot P means the scalar product of vector R and vector P, plus iota times H cross times vector R dot vector P, where again vector R dot vector P is the scalar product of the vector R with vector P, where, as mentioned earlier, vector R is the radial vector and vector P is the momentum vector, linear momentum vector. So if we rearrange these equations for operator L square, we can rewrite this equation for the operator, that is vector R dot vector P whole square is equal to vector R square times vector P square minus operator L square plus iota times H cross times within brackets R dot P, where dot refers to the scalar product, and the value of vector R dot vector P turns out to be equal to minus iota times H cross times R times within brackets vector R by R dot del operator, where vector R by R is simply the unit vector r, radial vector, unit radial vector, and dot is the scalar product, and del operator is I cap del by del x plus y cap plus j cap del by del y plus k cap del by del z, where I cap, j cap, and k cap are the unit vectors along the x, y, and z direction. And this turns out to be equal to minus iota times h cross times r times del by del r, or the partial differentiation with respect to the radial vector. We can then rewrite the relation for the operator L square as operator L square is equal to minus h cross square times r square times del operator square plus h cross square times within brackets r times partial differentiation with respect to r whole square plus h cross square times r times partial differentiation with respect to r. And this can be written as del square minus h cross square within brackets r square del square minus partial differentiation with respect to r times within brackets r square partial differentiation with respect to r bracket close. So on comparing these above expressions, we get the expression for del square as del square is equal to 1 by r square times del by del r, that is partial differentiation with respect to r, times within bracket r square del by del r minus 1 by h cross square times r square whole times operator L square. Now if we want to write down the same expression for the del operator in the spherical polar coordinates, or when we have replaced the value of the L square operator, then we get the value of del square as del square is equal to 1 by r square times del by del r acting on r square times del by del r plus 1 by r square times sine square theta times del by del theta acting on sine theta times del by del theta plus 1 by r square times sine square theta whole times double derivative of the partial differentiation with respect to phi, where the value of the L square operator is minus h cross square times within brackets 1 upon sine square theta times del by del theta acting on sine theta times del by del theta plus 1 by sine square theta time whole times double derivative of partial differentiation with respect to phi. Now let us discuss the eigenvalues and the eigenvectors of the operators L square and Lz. That means the z component of the orbital angular momentum operator and the L square component. So let us first start with the state vector Lm, and then we denote the eigenvector so that the eigenvector L square acting on the state vector or the ket vector Lm returns the value L times within brackets L plus 1 times h cross square times state vector or ket vector Lm. Here L square is the operator, ket vector Lm is the state vector, and L times within brackets L plus 1 times h cross square is the corresponding eigenvalue when the L square operator acts on the state vector Lm, and small l is the value of the orbital angular momentum number. Similarly, operator Lz, that is the z component of the orbital angular momentum operator or vector, acting on the state vector Lm returns the value mh cross times state vector Lm or ket vector Lm. Here operator Lz is the operator, ket vector Lm is the state vector, m times h cross is the corresponding eigenvalue for the eigenvector or the ket vector Lm, and m is the magnetic orbital angular momentum number. Here one can see that the operators L square and Lz are both functions of the angles theta and phi in the coordinate representation, that is the spherical polar coordinate system. And so, because both operators L square and operator Lz are functions of angles theta and phi, therefore we can expect the eigenvectors as having spherical harmonics. So the bra vector r acting on ket vector Lm gives the spherical harmonics y Lm within brackets theta phi, where y Lm is the spherical harmonic for the functions theta and phi. And using the above equations, we can rewrite the above equations in terms of the spherical harmonics as minus iota times h cross times partial differentiation with respect to phi acting on y Lm theta phi is equal to m times h cross times y Lm theta phi, which means that if the operator minus ih cross partial differentiation del by del phi acts on the spherical harmonic function y Lm theta phi, it returns the eigenvalue mh cross. Now if we integrate with respect to the angle phi, we get the value of the spherical harmonic as y Lm theta phi is equal to f Lm theta exponential to the power iota times m phi, where f Lm is independent of phi. The admissibility condition of the wave function requires that the spherical harmonic y Lm theta phi satisfies the periodicity condition y Lm theta phi plus 2 pi is equal to y Lm theta phi, which means that the spherical harmonic y Lm theta phi is periodic in phi with a periodicity of 2 pi. Eigenvalues of the operator L square and operator Lz. Now, using the periodicity of the spherical harmonics, we can finally see that if we implement this condition of periodicity, that phi is periodic with a periodicity of 2 pi, then this implies that exponential to the power iota times m phi is equal to exponential to the power iota times m whole times within bracket phi plus 2 pi, and this condition of periodicity will be satisfied or will be true if and only if exponential times iota m times 2 pi is equal to 1, where m is an integer, that is m can take values 0, plus minus 1, plus minus 2 and so on, and the largest value that m can take is L. So if L has values going from 0, 1, 2 and so on till infinity, then m can take values from minus L plus 1 and so on till 0, 1, 2 and so on till L minus 1, L. Here it is important to note that in case of the orbital angular momentum, only the integral values are allowed, which is unlike the general case of spin angular momentum. Now, in order to determine the function FLM, which we came across earlier while defining our spherical harmonic YLM theta phi, we solve the equation operator L square acting on spherical harmonic YLM theta phi and this gives the value h cross square times L times within brackets L plus 1 whole times y lm theta phi, where h cross square times L times within brackets L plus 1 is the eigenvalue corresponding to the operator L square acting on the spherical harmonic y lm theta phi. And here we have also used the spherical representation of the operator L square and have substituted cos theta is equal to xi. The operator L square in the spherical representation and substitute cos theta with xi, then the equation is reduced to within brackets 1 minus xi square whole times double derivative with respect to xi minus twice xi times derivative with respect to xi plus within brackets L into L plus 1 minus m square upon 1 minus xi square whole bracket closed times omega Lm xi as a function of xi equal to 0. So this is a second order differential equation, and this second order differential equation in xi can have two solutions. These solutions are given by PL xi and QL xi, where PL xi and QL xi are the solution of the Legendre's differential equation, and PL xi and QL xi are referred to as the Legendre's polynomials of the first and the second kind. So using this definition, we can write down WLM superscript 1 as a function of xi is equal to PLM xi, and this is equal to within brackets 1 minus xi square whole to the power m by 2 mth derivative of PL xi with respect to xi, and similarly WLM superscript 2 xi is equal to QLM xi, and this is equal to within brackets 1 minus xi square whole to the power m by 2 times mth differentiation or derivative of QL xi with respect to xi. So here WLM superscript 1 xi and WLM superscript 2 xi are the solutions to the Legendre's differential equation corresponding to the Legendre's polynomials of the first and the second kind respectively. And we can write down the general equation of the Legendre's differential equation as bracket open within brackets 1 minus xi square times double derivative with respect to xi minus twice xi times derivative with respect to xi plus L times L plus 1 bracket closed whole times WL xi is equal to 0. Here we see that the second function is not acceptable as a solution since it is not finite at all points defined from minus 1 is less than equal to xi is less than equal to 1. Therefore, the solution that we will retain is only the first function, that is WLM superscript 1 xi. Eigenvectors as spherical harmonics. So from the earlier description, we find that the eigenvector bra vector r ket vector lm is given by bra vector r ket vector lm is equal to y lm theta phi is equal to CLM PLM cos theta exponential to the power im phi, where CLM is the normalizing or the normalization constant and which has to be determined by using the condition or the orthonormality condition, that is bra vector lm ket vector lm is equal to integral y lm theta phi star y lm theta phi d omega is equal to 1. Using this orthonormality condition or the normalization condition, we get integral y lm theta phi star y lm theta phi d omega, that is the integration over the entire volume, phase space volume, gives modulus of c lm square whole square times integration with limits from -1 to +1 within brackets p lm cos theta whole square d of cos theta times integration with limits from 0 to 2 pi exponential to the power minus im phi exponential to the power im phi d phi, and this gives us the final result as integral y lm theta phi star y lm theta phi d omega is equal to modulus of c lm whole square times 4 pi by 2l plus 1 times L plus m factorial upon L minus m factorial. Here it is important to remember that L is the orbital angular momentum number and m is the magnetic angular momentum number. And using all these equations, we finally get the value of the normalization constant CLM as modulus of CLM is equal to, within brackets, 2l plus 1 by 4 pi times l minus m factorial upon l plus m factorial whole to the power half, or CLM is equal to exponential to the power iota times delta times square root of 2l plus 1 by 4 pi times l minus m factorial upon l plus m factorial. Representation harmonics. In the preceding steps that we have just discussed, we have used the orthogonality relation integral PLM PL prime m d xi is equal to 2 upon 2l plus 1 whole times l minus m factorial upon l plus m factorial times delta l prime, where delta is the del operator. Here the factor exponential to the power iota times delta is the phase which is chosen such that exponential to the power iota times delta is equal to -1 to the power m. Using all these relations, we can see that the final solution that is obtained in the form of spherical harmonics is given as y lm theta phi is equal to -1 to the power l plus m bracket open 2l plus 1 by 4 pi times l minus m factorial upon l plus m factorial bracket close whole to the power half times PLM cos theta exponential to the power im phi, where PLM cos theta is the Legendre's polynomial and YLM theta phi is the spherical harmonic. And this can further be solved as YLM theta phi is equal to -1 to the power L plus m times 1 upon 2 to the power L times L factorial times bracket open 2L plus 1 by 4 pi times L minus m factorial upon L plus m factorial bracket close to the power half times sine to the power m theta times d by d cos theta whole to the power m plus L plus m times sine to the power 2L theta times exponential to the power iota times m times phi. These two properties or these two relations of the spherical harmonics are the well-known and useful properties that are often used in quantum mechanics. Space quantization. Let us now interpret the results of the formulation, which can be summarized in the form of the following two equations. Operator L square acting on the spherical harmonic y lm theta phi is equal to h cross square times L into L plus 1 times y lm theta phi for L equal to 0, 1, 2 and so on, where L square is the operator, y lm theta phi are the spherical harmonics, h cross square times L into L plus 1 is the corresponding eigenvalues for the operator L square acting on the spherical harmonics y lm theta phi. The other equation is that of operator Lz acting on the spherical harmonic y lm theta phi. So operator Lz, that is the z component of the orbital angular momentum operator acting on the spherical harmonic y lm theta phi, gives h cross square m y lm theta phi for m ranging from minus L plus 1, so on, 0, 1, 2 and so on, L minus 1 and then L. Here Lz is the operator, y lm theta phi are the eigenvectors and or the eigenfunctions, and h cross m is the corresponding eigenvalue, where m is the magnetic quantum number and h is the Planck's constant. The later one, that is the second equation, due to the operator Lz, states that the z component of the angular momentum can take only discrete values, integral multiples of h cross, that is, in integral multiples of h cross, because m takes only integral values. This is in fact a quantum mechanical statement of space quantization. From experimental standpoint, any observation designed to determine the z component of the orbital angular momentum operator Lz can give only the result mh cross, where m is the magnetic quantum number. It is known that when an atom is subjected to a magnetic field whose direction is conventionally taken along the z-axis, it causes the energy of the atom to change by an amount proportional to the z component of the magnetic moment, which in turn is related to the z component of the orbital angular momentum number operator Lz. Thus, space quantization manifests itself through discrete changes in atomic levels in the presence of magnetic field. That is why the quantum number m is called the magnetic quantum number. The 2L plus 1 fold degeneracy for any given value of L shows that there is underlying symmetry according to which any direction in space is as good as any other. The existence of symmetry makes it possible to have different ways of using the commutation relations. Ladder operators. First, let us discuss what is a ladder operator. So a ladder operator is typically an operator which either increments or decrements the corresponding eigenvector by an eigenvalue 1. So the ladder operator for the angular momentum operator can be written as orbital angular momentum operator L plus, which is the ladder or the up or the incremental operator for the orbital angular momentum, is given as operator L plus is equal to operator Lx plus iota times operator Ly, where operator Lx is the x component of the orbital angular momentum operator and operator Ly is the y component of the orbital angular momentum operator. And this turns out to be equal to h cross times exponential to the power iota times phi whole times within brackets del by del theta plus iota times cot theta del by del phi. Similarly, the down operator or the decremental ladder operator, orbital angular momentum operator L minus, in terms of the x and the y components of the orbital angular momentum operator is given as operator L minus is equal to operator Lx minus iota times operator Ly, and this is equal to h cross times exponential to the power minus iota phi times within brackets minus del by del theta plus iota times cot theta times del by del phi. So using the general properties of the spherical harmonics that we have seen earlier, one can show that the ladder up operator of the incremental operator L plus acting on the spherical harmonic y Lm theta phi is equal to bracket open L into L plus 1 minus M into M plus 1 bracket closed whole to the power half times y L M plus 1 theta phi. So here we see that there is an increment in the value of M from M to M plus 1 when the operator L plus acts on the spherical harmonic, and the corresponding eigenvalue is given by bracket open L into L plus 1 minus M into M plus 1 bracket closed to the power half. Similarly, the ladder operator L minus, that is the decremental operator L minus, acting on the spherical harmonic y Lm theta phi is equal to bracket open L into L plus 1 minus M into M minus 1 bracket close whole to the power half times y L M minus 1 theta phi, which means that when the decremental ladder operator L minus acts on the spherical harmonic y Lm theta phi, it returns the corresponding eigenvector y L M minus 1 theta phi with eigenvalues bracket open L into L plus 1 minus M into M plus 1 whole to the power half. And it follows that using the general properties of the spherical harmonics, we can get integral y star L prime M prime operator L plus acting on y L M d omega is equal to bracket open L into L plus 1 minus M into M plus 1 bracket close to the power half delta L L prime delta M prime M plus 1, where delta LL prime would give 1 if L is equal to M L prime, and delta M prime M plus 1 would give a 1 when M prime is equal to M plus 1. Similarly, integral y L prime M prime star operator L minus acting on y Lm d omega is equal to bracket open L into L plus 1 minus M into M minus 1 bracket close to the power half delta L L prime delta M prime M minus 1, where delta LL prime returns 1 if L is equal to L prime and 0 if L is not equal to L prime, and delta M prime M minus 1 returns 1 if M prime is equal to M minus 1 and returns 0 if M prime is not equal to M minus 1. So to summarize, we can write integral y L prime M prime star operator L plus minus y Lm is equal to the expectation value of the operator L plus minus with respect to the state vector Lm, and is given by bra vector L prime M prime operator L plus minus acting on ket vector Lm. So students, let us now summarize all that we have learnt in this module. So whatever we have learnt can be put as follows. Firstly, we learned about how to represent the orbital angular momentum operator in spherical polar coordinates. Then, after having learnt that, we then tried to find out the eigenfunctions and the eigenvalues that are associated with the operators L square and Lz of the orbital angular momentum operators. in doing so, we then found that we have to use spherical harmonics. And in order to be able to use spherical harmonics, we then studied the important properties of spherical harmonics, most notably that we have a periodicity in the different components that we are using in this spherical polar coordinate system. And then we went on to understand the physical interpretation of the eigenvalues of the orbital angular momentum operators L square and Lz. From there, we moved on to writing down the eigenvalue equations for the ladder operators of the orbital angular momentum operators, that is, operators L plus and L minus. And we also found out what were the corresponding eigenvalues corresponding to the ladder operators and the eigenvectors or the state vectors. Thank you.